Today I'll be summarizing some of my recent work on the topic of fast angles-only relative navigation using polynomial dynamics. So let's start off by motivating and defining the problem. So by angles-only relative navigation, I mean estimating the motion of a target space object with respect to a spaceborne observer using only bearing angle measurements. This is an extremely attractive paradigm because it makes use of sensors such as star trackers that are already ubiquitous in satellite applications. It's also passive and doesn't rely on cooperation from the target object. The main challenge associated with angles-only navigation is a range ambiguity that arises when using linear translational state dynamics models, which predict the same bearing angle behavior regardless of the range to the target spacecraft. The particular problem that I'm focusing on today is initial relative orbit determination, or IROD. So we have a set of line-of-sight measurements from the observer to the target represented as unit vectors in the observer's radial transverse normal, or RTN, coordinates. We also have knowledge of the observer's absolute state, and we want to find the vector of constants that characterize the target's relative state, which I'll call C. In order to link the unknowns to the knowns, we use a dynamics model that maps C to the components of the relative position vector delta R. The line-of-sight vector has to be parallel to the relative position vector, so we can use the fact that their cross product is 0 in order to obtain a set of constraints of the form shown here. Now, each measurement provides 2 linearly independent constraint equations, so at least 3 observations are needed to fully determine the 6-dimensional relative state. And now we can actually better understand the range ambiguity problem. If our dynamics model is a linear mapping from the relative state constants to the position coordinates x, y, and z, then the constraint equations are also linear, represented as a vector inner product. And we can compactly write the 6 constraint equations as a homogeneous linear system. And since this relative state vector lies in the null space of the constraint equation matrix L, multiplying it by any scale factor will lead to a valid solution to the constraint equations. So several methods have been studied to resolve this range ambiguity problem. The most intuitive strategy is to simply change the observer's viewpoint by performing a maneuver. This effectively simulates binocular vision with the obvious drawback of consuming precious propellant. Another strategy is to capture the nonlinear effects of range in the exact transformation to a state representation, such as ROE. The main disadvantage of this approach is that you need measurements over an extended period in order to tease out the range effects, resulting in a slower process. The work that I'm presenting here is motivated by a third strategy, which is to use a higher order mapping between the orbital element state and the translational state in order to resolve the range ambiguity. And we can introduce the minimum amount of nonlinearity by simply extending our relative dynamics model to second order. So each of our constraint equations then becomes the sum of a linear term with a quadratic form. Unfortunately, unlike linear systems, higher order polynomial systems don't have general solutions. Instead, they must be solved by numerical root finding techniques such as Newton-Raphson or the more specialized method of homotopy continuation. And while these are powerful tools for solving a broad class of problem, they can be computationally expensive and require initialization. So one of the main contributions of the work that I've done for this presentation is a more efficient solution approach that is tailored to the IROD problem that I've just defined. But before I get to that, I would like to quickly highlight the other main contribution of this work, which is the relative dynamics model that I'm employing. So I have chosen as my relative state the set of quasi-non-singular relative orbital elements. These consist of the relative semi-major axis, relative mean longitude, and components of the relative eccentricity and inclination vectors, as defined here. So for near circular orbits, these are equivalent to the integration constants of the Kolesi-Wiltshire model and have a clear relationship with the relative orbit geometry in the RTN frame. So for this work, I've introduced a new second-order model based on a series expansion of the exact transformation from ROE to RTN coordinates. The use of ROE as the relative state constants naturally integrates this work into the body of literature on ROE-based GNC algorithms, as well as opening the door to incorporating perturbation effects into the proposed relative navigation scheme through existing state transition matrices in ROE space. Now, the inclusion of second-order terms leads to an accurate mapping at low computational costs, and in the context of angles-only IROD, allows us to encode range information into the system of polynomial constraint equations. So next, let's look at how we can go about solving that system. Thinking about the problem a little bit more generally, we have n equations that consist of the sum of a scalar, a term that's linear in the unknowns that we're trying to solve for, as well as a quadratic term. So now my solution approach is based on two insights about our problem. First, the magnitude of the ROE scale roughly with the ratio of the interspacecraft separation to the orbit radius. So for practical scenarios, we expect the relative state constants in the vector C to be very small. Second, our dynamics model is just that, a model. So we don't expect the solution of our system to exactly reflect the true relative state. These insights motivate an approximate solution approach where we can use a quadratic formula to solve any of the equations in our system for one of the unknowns. And then assuming we're solving the nth equation for the nth constant, we have two solutions which depend on the remaining n-1 constants. Since we expect terms involving the relative state constants to be small compared to the terms which depend only on the constraint equation coefficients, we can expand the radical as a Taylor series and truncate terms higher than second order. This gives us a second order expression for the nth constant in terms of the remaining relative state parameters. We can then use this to eliminate that constant from the other constraint equations of our system. And repeating this process recursively, we end up with a single equation and one unknown that we can solve and back substitute to find the full set of relative state constants. Now, each application of the quadratic formula leads to two solutions. So we end up with a branching tree, which ultimately produces 2 to the n estimates of the relative state. However, many of these branches violate our approximation assumptions, and we can actually leverage the structure of the tree to prune those invalid branches and reduce the computational cost. So the constraint equations governing the IROD problem are homogeneous, and so all of the scalar terms, at least in the initial system, are actually 0. This tells us that one branch of the tree will directly lead to the trivial solution, which would place the target spacecraft in the same state as the observer. The magnitude of the estimated relative state constants tends to increase as we move away from this trivial branch until our small value assumption breaks down. Thus, only a small number of the adjacent branches really need to be considered. Altogether, this gives us an efficient algorithm for finding infinitesimal solutions to polynomial equations by quadratic truncation and elimination recursion, which I'll call the InSPEQTER algorithm. To demonstrate its effectiveness, I've shown estimation errors for a large set of randomly generated sample systems with roots ranging over several orders of magnitude. So the error in the estimated constant vector is approximately cubic in the magnitude of the largest solution element, scaling with the lowest order of the truncated terms in the InSPEQTER algorithm's approximations. Now, as expected, solutions with roots close to unity are poorly estimated, but in the range representative of ROE in practical mission scenarios, the solution estimate is much more accurate. And we can actually refine the solution estimate by iteratively modifying the system of equations to solve for the error in the previous estimate. So here I show the results after one iteration. And we see that after 3 iterations, the algorithm has essentially converged to numerical precision for nearly all test cases within the valid range. So it works very well with these purely mathematical test systems. But next, let's look at some validation results when we combine the InSPEQTER algorithm with the new second-order ROE model and apply them to simulated relative mission scenarios. So for our proof of concept, I'll assume the true dynamics are Keplerian and neglect the uncertainty in the measurements and knowledge of the observer's state. So the plot on the left shows an example scenario in highly elliptical orbit with line-of-sight measurements taken at 5-minute intervals. The black trajectory shows the true relative motion in the RTN frame, while the trajectory shown in red is the prediction of our second-order dynamics model using the state estimate obtained from the InSPEQTER algorithm. The two match to within the resolution of the figure, providing a qualitative validation of both the model and the solution approach. For a more quantitative assessment, I looked at 10,000 scenarios with absolute and relative state parameters randomly sampled from a representative range, with interspacecraft separations from hundreds of meters to hundreds of kilometers. So the histogram here on the right shows the distribution of relative errors in the initial estimate of the relative state constants, as well as in the final estimate after refinement. So while refinement does shift the distribution toward lower errors, it is less effective here than in the cases that we looked at before, because now the true relative state differs from the exact solution to the polynomial constraint equations. Nevertheless, typical errors are on the order of 10 to the minus 3 or 0.1% for both distributions, with very few scenarios having errors larger than about 10%, which means that we're giving a good initial estimate for something like sequential filtering. A major challenge of IROD based on polynomial dynamics models is the sensitivity to error in the bearing angle measurements. So the modeled and measured bearing angles might differ due to perturbations in the space environment, error in the observer's state estimate, as well as random noise. But an important class of these errors can be represented as a systematic bias in the measurements, essentially causing a small rotation of the line of sight vectors. We can account for this type of error in our IROD methodology by introducing a linearized rotation into the construction of our constraint equations and estimating the small angular biases represented by phi1 and phi2. Since this increases the size of the vector that we're estimating, additional measurements will be needed to determine the system. But this plot of relative error in the estimate as a function of the maximum bias angle demonstrates the reduction in sensitivity that is achieved by this small modification to our system. So to summarize, the two key contributions of this work were the introduction of a second-order mapping from ROE to RTN coordinates and the introduction of the InSPEQTER algorithm for efficiently solving the resulting IROD constraint equations. We also saw how this approach to angles-only IROD performs across a wide range of relative motion scenarios, and how it can be modified to reduce the sensitivity to bias in the bearing angle measurements. The path forward is to address errors arising from perturbations and noise by supplementing the ROE dynamics model, as well as sampling the measurements. And the improved methodology can then be validated in high-fidelity simulations with hardware in the loop, providing a major step towards flight demonstration of an autonomous angles-only navigation system for the next generation of multi-satellite missions. Thank you. With that, I will take any questions.